Hi, this lesson is on latent heat. And what latent heat is the energy gained or lost during a phase change or a change of state. So in other words, when ice is melting or freezing, that's a change of state. The temperature doesn't change during the phase change because all the energy is used to change the state. So the formula is going to be a little different. So let's write that down. The temperature does not change during a phase change because all the energy is used to change states. Okay, so let's do an example. We're going to use the example of water. We're actually going to melt water, or in other words, melt ice, and we're actually going to heat it all the way till it turns into a vapor. All right, so for example, we're going to suppose we are going to melt ice and heat it to a water vapor state. In fact, when you go from ice, directly from ice to a vapor or a gas, that's called sublimation. So we're doing, I guess, the worst case scenario. Okay, so let's visualize this. Pretend you are actually boiling ice. I guess most people don't boil ice, but we're going to do that. We're going to boil ice, and we're going to actually graph what's going to happen to that ice as it turns into water, and then so on. All right, so most of the time, when you take ice out of the freezer, it's approximately negative 20 degrees Celsius. So a lot of people think, oh, I'm going to stick ice or freeze ice, and they just assume their freezer is at 0 degrees. Well, no, that's not very cold ice. Ice will be a liquidy, watery mixture, so you actually want it below 0. So most freezers are typically negative 20 degrees Celsius. So we're going to start our graph here. And so you'll notice that here I have temperature. We start at negative 20. This is your freezer temperature. And when you take ice out, it's at that temperature. It's got to warm up. And typically when you boil it at a, or cook ice, which most people don't, it does warm up at a linear rate to about 0, and then it starts melting. So really what's happening is the ice actually has to get to 0 degrees before it melts. So you've got this warm-up period, and then it melts. All right, so this here is what I mean by the energy or the temperature does not change during a phase change. So right here, the temperature does not change during a phase change because all the energy is used to change states. In this case, when ice is melting, it will stay at 0 degrees until it fully, completely turns into water. Once it turns into water, then you're cooking water. And we all know water boils at, let's say, 100 degrees. That's for a standard atmospheric pressure. So you'll learn more about that in chemistry class. Okay, so we are warming up the water. So let's actually label these phases or these stages. So you have section A, and section A, you need to warm up the ice. Then section B, you are melting the ice. Section C is you are warming up the water. So I'm going to actually add this, melting the ice to water. We'll add that so you know there's a phase change, okay? And then see, we're warming up the water, and then when it hits 100, it boils. Now, what boil actually means is, well, it's turning into a liquid to a gas. So there's another change of state going on here, and that is for section D. So D, we have boiling, all right, from water to gas. And then if this pot that you're, I guess, cooking the stuff in, the ice, is all contained, technically what happens is then the gas will warm up, and that's where you get the steam, those steam cookers, right? There's the steam that's actually cooking your food, and that's actually higher than 100 degrees. So it's really, really hot. Extra hot, let's say, all right? And that is section E, and you're going to now warming up the gas, okay? I spelled warming funny here, perfect. All right, so warming up the gas. And those are the stages of, I guess, the phase changes. The phase change is technically B and D are the phase changes, whereas A, C, and E are just warming up stages. Now, you can also go backwards as well. So basically, when you go backwards, you're going to put, I guess, this gas in a freezer, for example, so get some water vapor, and you can actually cool it down. It will go the reverse way, so it's goes both ways, melting or freezing. All right, so let's do an actual summary. I'll get back to this graph in a moment, and we'll fill more in. But let's go back to a summary of what I talked about, this phase change. So latent heat, there actually are two formulas for it, but this is a general formula for latent heat. E is equal to mL, okay? mL, and you'll notice that there is no temperature. So we're only talking about B, which is over here. This is the latent heat formula you would use because there's no change in temperature, just a change in state, and also D. All right, now it applies to both, and I'll explain why or how. So there's actually two types, like I said. There is this type called diffusion, latent heat of fusion, and the formula looks like this, mLF. Okay, so same formula except there's a subscript. Fusion technically means solid to liquid or liquid to solid. Okay, so that's the formula you would use. Whereas the other type of formula is latent heat of vaporization. Vaporization. Okay, so that is when you go from liquid to gas or gas to liquid. And the formula here is E is equal to mLV. So same formula with the subscript. What the subscript means is that you have to look up these values, just like heat capacity. Specific heat capacity is discovered through experiment, and same with latent heat. So you look up in a chart, and here's the chart. Again, fusion, you would use this one, and this would only apply to melting or freezing. This one would be applied to boiling or condensation, so vaporization. If you look at the formula sheet as well, you have the latent heat of fusion. Here's the fusion ones, and here are the latent heat of vaporization ones. Okay, so I also gave melting and freezing points and boiling points and condensation points if you need it. But we all know that water, and we typically I use water as an example. Water freezes and melts at 0 degrees and boils at 100. Okay, so let's continue. There's a little bit more to this formula, and that means there's also a plus sign or there is a minus sign to this formula. Okay, the plus sign to this formula means that you're warming the object up. Okay, the plus sign in vaporization means you're boiling. So in this case, this means melting. Okay, and this here means boiling or evaporation. Okay, the other negative, what that means is you're going the other way backwards. So you're freezing, all right, or you're condensing. Condensation. All right. Okay, so latent heat of fusion. So far we have this type, melting or freezing, or latent heat of vaporization, boiling or condensation. And it's denoted either by a plus or minus. All right. Lastly, let's look at units. You know energy has to be in joules. Okay, so you have joules for energy. Mass, you know, is already in kilograms. And latent heat, well, what are the units? Well, you know you need joules at the end, and you got kilograms, so you need to cancel out the kilograms to get your joules. So latent heat has to be joules per kilogram, which makes sense. The more ice you have, the more energy you need to melt it. All right, and that's why that's a unit for latent heat. All right, let's do an example and get some numbers involved. All right, so here we are starting with an example. We're going to melt ice. In fact, we're going to sublimate it. So we're actually going to do this example with the graph. We're going to take ice and we're going to turn it right into water vapor. So you're going to sublimate 2 kilograms of ice at negative 19 degrees to 110 degrees Celsius. How much energy will that take? Well, that's a great question. All right, so let's figure out how much energy that will take to do this. First, I like to draw a picture so you can visualize what's going on, or you could do a graph like we've done up here, like over here. Same thing. Okay, let's actually draw a picture. So I have ice, and I have to warm it up, and then it melts, and then I have to warm up the water, and then it boils, and then I have to warm up the steam. Okay, now according to this picture, I have 1, 2, 3, 4, 5 formulas or 5 stages that is in my picture. That's the same thing as the graph. I have 5 stages, so therefore I'll need 5 formulas to do this, all right? Okay, so let's do it. 5 formulas. Technically, I'll label them A, B, and C so you can relate it to the graph. So this is stage A, this is stage B, C, D, and E. Okay, perfect. All right, I'm going to start a new page over here so you guys can see all my lovely calculations. I'm going to write out the stages here. A, B, C, D, and E. All right, stage A, we are warming up ice. Now, when you warm up ice, the temperature does change, so we have to use this formula over here. Okay, when you use this formula, it's a 2 kilogram ice. The heat capacity, let's look up for ice. Heat capacity for ice. Where are we here? 2100. Okay, Remember, it's not water, it's ice. So you got to look up for ice. So 2100, and then the temperature, we are going from, the final temperature is 0, minus, and then negative 19. And that works out to be 79,800 joules. Okay. Next, stage B. Remember, stage B is latent heat, right? It's a phase change, which are highlighted or circled in the blue. So you have to use a latent heat formula. All right, so the latent heat formula, I'm going to have MLF. It's a fusion because we are melting. 2 kilograms of ice, and let's look up the latent heat of fusion. Okay, latent heat of fusion, where did it go? I've got water. Here it is. So that's 3.3 times 10 to the 5, or 3.3 times 10 to the 5. And if you multiply those two together, you're going to get 660,000. There you go. Okay. B, or we just finished B. C. Let's do C. This is going to be MC delta T because we're warming things up. Again, temperature change. So that's 2 kilograms. Water is 4,200. You're looking that up on the chart. Let's double check to make sure. So water. Here, 4,200 right there. All right, and then the temperature is going from 0 to 100 degrees, so 100 minus 0. Working that out, wow, that takes a lot of energy to boil water. There we go. All right, D, we're going to boil the thing, or actually warm it up. Now we're boiling it. When we're boiling it, you're doing a change of state, all right, and so that's... in blue, we have to do latent heat of vaporization, MLV. 2 kilograms that we're vaporizing. So let's see, vaporization. Let's look that up. And we have, okay, there it is, 2.3 times 10 to the 6. 2.3 times 10 to the 6. And wow, that's a lot of joules. We're up to 4 million joules to vaporize some water. Okay, now once it's steam, we're going to warm up the steam. So that's 2. Let's look up what steam is. Okay, do I have steam on here? Good. Oh, here we are. Steam, 2,000. Okay, so 2,000. Oh, there we go. And then we have the final temperature is going to be 110 minus 100 is the initial temperature of the steam, and that will be just 40,000 joules. Okay, so this is the energy of each stage. Whoa, you're going to add all these up. All right. I'm going to switch markers because my other marker is running out of juice. Okay, so here we're going to add up all the energies. All right, so we add up all the energies, and it's going to be 6,219,800 joules. Whew, that's a lot of energy to boil ice. This is probably why we don't boil ice, we boil water. All right, so there it is. So this is the individual stages, all right, and that's the actual calculations. If you want, you can even write down the individual formulas for each one and work it out in your graph if you like. You'll notice anything with a slope, a non-zero slope, is going to be is equal to MC delta T. Anything that's flat, which is circled in the blue, will be ML, like so. All right, so that is basically how to change state. Next lesson, I'm going to combine the two. We're going to actually do a heat exchange with a change of state. All right. See you next time. Bye.